The radiation density perturbation of the early universe eventually makes the make microwave background replace the CMB after the photon decoupling. And this CMB contains many informations of the universe, like the how many the its components that exist in the universe, and we can extract the various quantity by the CMB fitting. And the CMB is the almostly isotropic with the temperatures of the 2.73 Kelvin, but there are still the anisotropy with the small temperature fluctuation with order of the 10 to the minus 5. And these tiny fluctuations includes information about the primordial perturbation. So in the previous discussion, we talk about how the cosmological perturbations arise with the two components, matters and the radiation. And the radiations eventually pass through the CMB. The temperature fluctuations can be described by the delta T over the T2 for some specific directions and this temperature fluctuation can be expanded through with the basis of the spherical harmonics. And here the angular momentum index L represents the scale of the fluctuation. So the mode L corresponds to the angular scale theta as pi over the L. So if the L is small, then this means the angular scale become large, while the for large L, this corresponds to the small angular scale. And the cosmological perturbations satisfies the statistical isotropy, so the expectation values such as 0, but the two-point correlation functions yield some specific quantity CL, which is called the angular power spectrum. And this represents the variance of the temperature fluctuation at the multipole L. And usually we assume that the natural estimator CL hat as a summation of the coefficient of the temperature fluctuation with some normalization factors. Then this estimator or the angular power spectrum becomes related with the 2 points correlation function. Now because the this temperature fluctuations expanded in terms of the spherical harmonics, and if we calculate this correlation function, that this yields just a Legendre transformation, because with sums over the Archimedes angular momentum index small m, and by replacing the summation to the integration, we can obtain the relation between the power spectrum for the multipole L mode and at the scale of the theta. So the important quantities in the logarithm interval L and L, the quantity becomes the L times L plus 1 over 2 pi times the CL. So the now all the information of the temperature fluctuations of the CMB anisotropies are encoded in the angular power spectrum CL. And this CL can cluster over the angular momentum index L. And to analyze how the informations are encoded in the angular power spectrum, both of all there are many acoustic peaks in the CL. This acoustic peaks comes from the photon baryon fluid. Already we discussed before. So before the recombinations, the photon and the baryons are tightly coupled each other via the Thomson scattering, and they effectively behaves like as a single fluid. And the photon has a project with one of those of the energy density. So this project resisted about the gravitational collapse, but the gravity tends to the compress to the upper density regions. So the perturbations of the photon baryon fluid suffers acoustic oscillation, already we discussed before. And the photon density perturbations that follows these equations, the delta R, delta gamma, the photon density perturbation, this term corresponds to the speed of sound, which arises from the process. On the right-hand side, this is gravitational potential. And for the photon baryon fluids, the speed of sound is given by the some functions of the ratio between baryon energy density and the photon energy density. Then we can obtain the some photon density perturbation delta gamma as the functions of the K mode, the solution of the equations, and also the functions of the sound horizon Rs, which is defined as the integrations of the speed of the sound over the confinement time. And when the photons and the baryons decouple at the recombination at the star, the oscillations are frozen and the sound horizon becomes fixed. So there will be some specific pace which becomes that this acoustic oscillation amplitude becomes the 0 at the star. So if the mode satisfies this KRS becomes the n times the pi, then this become cosine has some maximum and the minimum value. So this extreme oscillation correspond to the acoustic peak in the angular power spectrum of the CMB. And if we project this angular peaks to the specific angular scale by using the relation between the L and the theta, then we can obtain the some characteristic multipole scale for the acoustic peak. So the sound horizon at the recombination when the photon and the baryons are decoupled, this gives acoustic peak from the BAL signature in the observed CMB power spectrum. Now we turn to the other effects on the CMB. The temperature isotropies can arise from the gravitational effect, because the photons that climb out of some gravitational potential, then it loses energy when they climb up this gravitational potential well. And this produces the temperature fluctuations in the observed the CMB radiation. Such a gravitational rad shift called the Sachs-Ulfsen effect, briefly the SW effect, when the photons last scattering surfaces occur. So the temperature fluctuation from this Sachs-Ulfsen effect is just proportional to the gravitational potential. And this occurs very early in the universe when the photons surface the last scattering. But also the photon travels through the cosmic evolutions with the time dependence gravitational potential, and this gives the last steps of the blue shift. And the temperature fluctuations from this time dependence gravitational potential is called the integrated Sachs-Ulfsen effect, briefly the SW. So if we integrate the time dependence gravitational potentials over the conformal time, after the recombination to the some specific presence the component time, then this gives the contributions of the temperature fluctuations of the ISW. And such a time-dependent potentials occurs when the capital pi, this gravitational potential, or the material perturbations potentials changes, and this occurs when the universe transits from the radiation to the matter's dominant at the as early ISW, and when the late time universe, the dark energy causes the gravitational potentials. This gives the late ISW. And the other effects for the temperature fluctuation is the Doppler effect due to the some motions of the observer of the source. So if we all the sum over this temperature fluctuation from the Sachs-Surface factor and the Doppler factor, and we can obtain the CMB anisotropy spectrum in terms of the angular power spectrum over the multiple L mode. So now I talk about the analysis of the CMB power spectrum. So first of all, if the L is small, this corresponds to the large angular separation, and the L is large, this means the angular scale becomes small. So for the large angular scale, L is smaller than the 100 here. The dominant contributions of the CMB anisotropy comes from the Sachs-Surface effect. Because for the large scale, large angular scale, this mode was still super horizon at the recombination. This means that the angular scales are too large, so it's larger than the Hubble patches. So the acoustic oscillations are still not developed because this moves in the super horizon. So the temperature fluctuations comes from the gravitational potential from the Sachs-Surface effect. So this makes the nearly flat plateaus in the low multipole here. And also we can see the very largest uncertainties because the angular scale is very large, so that we can only the viewpoints to extract to calculate the point correlation function. So the point is that at the low multipole, the CMB anisotropy directly blocks the primordial impulsion perturbation because the inertial for the acoustic oscillations due to the these modes that was still in the super horizons at a very early time. And there are minimal modification for the late time universe evolution. The intermediate regions R is larger than the 100 but smaller than the 1000s here. There's some peak. Because the specific L modes are under the horizon before the recombinations, so this get the photon baryon fluid with the acoustic oscillation. So this gives the many acoustic peak here. And also we can analyze the uncertainties for the small L. Already I mentioned we can evaluate the cosmic variance for the point correlation function because this is a large angular scale, so the uncertainty becomes large when the L becomes small, and intuitively this can be interpreted as for the large scale that there are a few points to extract, so the 2-point correlation function is the large uncertainty. And finally, for the small angular scale, for large L, R is the larger than the 1000th, photons are diffused and the Barnard techniques through the last scattering surface that smooths out the perturbation. So the effect of the acoustic oscillations averages out. This means that there is some last scattering surface here. And because the scale is quite small, so that we can average this over the small scale fluctuation. Such as approaches of the small scale anisotropy, small CL, is called the silk damping. So the angular power spectrum, the high multipole exhibits the rapid decline. So far we talk about the angular power spectrum of the CMB for the each scale and how this temperature fluctuations that lies, and also for the acoustic peaks from the BAO. Now talk about how can we extract the other information from the CMB. Because plus over the location of the acoustic peaks, the mainly is determined by the angular size of the sound horizontal recombination, and this sensitive the spatial curvature and the expansion history of the universe. And also the height of this acoustic peak, relative height, depends on the baryon density, because the baryon enhances the compression in the bottom baryon fluid. As the ladder mentions, the dynamics that determine the baryon energy density over the photon energy density. So the peak structures are determined by the baryon density parameters, omega b. The overall amplitude of the spectrum determined by the primordial density perturbation. And already mentions that the temperature fluctuation is the order of 10 to the minus 4 to 10 to the minus 5. So the primordial perturbation gives the scale of Robi, so the amplitude is 10 to the minus 10 now, and we can base the spectral index NS. So by feeding the theoretical power spectrum to the observed CMB data, we can determine the various parameters of the standard cosmology. For example, the baryon number density, matter number density, and Darkness number density, and the curvature and the Hubble parameters. And also we can define the additional parameters like as an effective, so-called effective number of relative species. This can be large if there is the extra radiation component or effective number of the neutrinos, because this can change the expansion light. So the acoustic structures can be modified. And also the primordial gravitational waves contribute to additional perturbations at a large scale, like as the B model of the CMB. So in the remaining time, I talk about what are these polarizations of the CMB by considering GW as a brief remark, not in detail. The cosmic microwave background radiations gets also the polarization. And this polarization can be described by the Stokes parameters Q and U, like as the optics. So this is also the same. The photons, the radiations, they propagate along the specific direction. And we can set the electric field or polarization EX and EY, the transverse plane. And the Stokes parameters define the time averaging of this EX and EY in a different combination. For example, the I is EX case plus EY case, and is time average, and also for the similarly for the Q and the U and V that can be defined. So I represented the total intensity of radiation, but the parameters Q and U that represented the linear polarization, and the V correspond to the circular polarization. And for the CMB, the Thomson scattering between the photon and the matters analyzes only the linear polarization, so the circular polarization vanishes with the V equal to 0. So the polarizations of the CMB can be completely characterized by the Stokes parameters Q and U, which represent the linear polarization. And these polarization fields can be expanded also for the spherical harmonics. And the coefficient can be classified as E mode and the pseudo-scalar B mode by defining the combinations of the coefficients with the plus and minus. And similar to the CMB analysis for the temperature fluctuation, we can reveal the polarization field from this coefficient. And also the angular power spectrum by using this coefficient of the E mode and B mode. So if we calculate the 2-point correlation functions of the E and the other E coefficient, this gives the angular power spectrum of the E mode, and for the B and B, this gives the BB mode. 2-point correlation function between the T and E, this gives the T mode. So by analyzing these different angular power spectrums of the E and the B modes, we can extract the polarization styles of the CMB. And we know that the scalar density perturbation only generates the E mode polarization, but while the tensor perturbations which arise from the primordial gravitational wave, it can produce both E and the B mode. So if we detect the B mode polarization of the CMB, then this can be evidence of the tensor perturbation. So in summary, we talk about the cosmic microwave background CMB radiations today. This can provide the powerful process of the early universe through the temperature and entropy. This includes many information. We define the temperature anisotropy or fluctuations, which can be expanded on as particle harmonics. And by analyzing its statistical property, we define the angular power spectrum CL over this multiple L mode. And this CL contains many information, but the large scale, the anisotropies that dominates by the gravitational impact, like as the Saxel-Puston and integral Saxel-Puston impact, because the mode lives in the super horizon, so their impacts, the light appears impacts is restrict. But for the intermediate scale, the mode in the sub-horizon, so the people that recombination, they get the acoustic relations of the photon barrier fluid, which yield the acoustic peak. And for the small scale, the photon diffuse report the combinations, and this plus the anisotropic, which called the silk damping. And the detailed shapes of the CMB power spectrum, like the relative amplitude or the height or the locations of acoustic peaks, are strongly depends on the cosmological parameters, like as the baryon number density, matter number density, and primordial perturbation. And in addition, CMB contains also the polarizations. It's only for the linear polarization type, and this can decompose in the E and the B mode. And for the B mode, this can be evidence of the gravitational wave. So today we talk about the cosmic microwave background. How can this include the various information of the universe, and actually that this CMB beatings the black and researches to bind some cosmological parameters that are underlying the standard cosmology.